Now we are going to start with shared memory one-sided communication. So as an outline of what we are going to see this time, this slide is presenting the way that MPI is providing access to shared memory communications since MPI 3.0. First of all, we will need to split the main communicator into shared memory islands using the function MPI-COM-SPLIT-type. And after that, we will define the shared memory window on each of those islands by using the function that we commented in the previous presentation on one-sided communications, which is called MPI-WinAllocate-Shared. The result of these calls by default is going to be a contiguous array that is accessible by all processes in the island. There are different parameters that we can tune there, so that we are going to see that there are different possibilities. But that's somehow the most common case. We need to be cautious that the memory that we are going to allocate may be already completely pinned to the physical memory of a process with rank 0. That means that we are not going to have the same situation of the first touch rule as in OpenMP, in which the first thread was getting assigned the physical memory if it was the first one that was writing a byte into one part of the memory. In this case, we are going to see that the definition of the window may already indicate the association to the physical memory. And well, in general, the access and synchronizations are going to be determined by normal assignments of the language. We are not going to have the put and get, but simple assignments to shared memory, and we are going to use the same synchronizations as in the one-sided communications part, for example the WinFence. As a motivation for the use of shared memory, we can indicate two main examples. The first one shown in this slide is the reduction of the memory space for replicated data. Just imagine in this case with a cluster of 3 SMP nodes without using MPI shared memory, which could easily represent the situation of let's say a large simulation system that is distributed into different processes and different domains in the so-called domain decomposition, and we are having halos with replicated data per each MPI process. If we are using shared memory, we can define the halos in a way that we only have once replicated data within each SMP node. Therefore, we can access the different halo data on each of the processes in just by storing it once and accessing it directly without more replication. That's one first advantage of an MPI shared memory, so that we don't have that much replicated data within one SMP node. And in general, the benefit is also to apply this as a hybrid way of making shared and distributed memory, of implementing shared distributed memory programming models, which in general we can do in 4 ways. We have a first way, completely MPI, not hybrid on every process, so that every core, every CPU is having halos for the whole system that we are simulating, and therefore MPI needs to use communication routines, MPI send and receive, within one node to communicate all these halos. The more optimal approach that was available is to use MPI and OpenMP. We can use a multi-threaded MPI processes so that inside one node we can have several OpenMP processes, OpenMP threads that are writing their shared data, and the halos are only necessary to communicate within MPI processes within the different nodes. And since MPI 3.0, we have the possibility to use MPI for distributed memory communications and MPI shared memory communication. That would imply that the halos inside one node can be implemented just by direct copying with C and Fortran statements, and just updating the halos conveniently without needing to perform a send and receive. However, we can even go one step ahead and then now implement the MPI communication within nodes and use MPI shared memory access inside one node, so that all of these SMP nodes can exchange information which would be before in the halo just inside the memory of the node, and the MPI processes would be effectively sharing the memory and the work within them in an analogous way to what OpenMP would have done. And this is an example of how it really works. You see in the upper part of this slide the MPI processes in orange that are assigned to the global communication COM-all, and they are having a rank that is defined by myRankAll. This is also indicated in the code below. Then, once we have the ranks in the original communicator, we can apply the MPI COM-split type call, so that we can define the subcommunicators inside each of the shared memory nodes. And this is done with the call that includes MPI COM-type shared as a tag for the split type, and also a 0 that is convenient to preserve the sequence inside the local communicators that was also derived from the main communicator. As you can see, the ranks that are generated for the internal subcommunicators are following the same order as the previous ranks from the main communicator outside the split type, before split type. Then once we get the new ranks inside the shared memory communicator, we are allocating the shared memory with the MPI win allocate shared function, so that we obtain the window and also the base pointer to the local memory that has been allocated as a window, which is indicated in the picture above in green. As you can see, this green memory is defined as a whole contiguous memory, shared memory chunk inside each of the SMP nodes. Therefore, each of the nodes is having a piece of memory that is consecutive in terms of physical memory, and every chunk is going to have a base, the same base pointer reference for it. And just a remark, as it appears in the slide, that for Fortran, after the WinAllocate is shared, it would be needed to convert the pointer of the buffer into a usable array. So when we have this access, we have created a shared memory that is contiguous across ranks, so that when we are inside one SMP node, we can address the last byte of rank I-1 as the one that is coming right before the first byte of rank I. That means that we are really having an array that is physically one after the other. And we can calculate for every process the offsets with only having the base pointer that we commented before from the window allocation, and just offsets from it. The use of RMA operations is not necessary, but just load store is fine. However, we need to take care that the process, in each process inside a communicator, is accessing the same physical memory, but actually the virtual address of the whole array may differ with the different processes. It's important to note this because we have processes that are having its own memory in the end. Even though we are having shared memory, we are still working with processors. So we are effectively not being able to ensure the same references between the different processors. Therefore, what we need to take care is that we don't use the addresses, the virtual addresses, as a reference when we try to communicate with other processes. One clear example is if we try to create linked lists. If we want to build a shared memory array with linked list information, we cannot really put the references in that array, but just or not the binary pointer addresses, but the offsets within the shared memory array. The base pointer should be kept as the main reference, and then the offsets with respect to it will be the ones that will give the correct value for all the processes. So we are seeing here an example on how this is working for the case that we want to print the values of one array the neighbor of each of the elements within one shared memory node. We are going to create the window as indicated in the same way that we did before, and if we want to know which are the values that are stored by the neighbors, we need to first synchronize to make sure that we are synchronizing inside the shared memory node every window inside the shared shared memory node, and we can then update the values of the base pointer inside it. Later on, we can synchronize again to make sure that the local window has been updated properly, the base pointer array, so to say. And after that, we can refer to the neighbor's rightmost value, as long as we are not the leftmost value, as the base PTR minus 1. And we can refer the right neighbor's leftmost value with referring base PTR and the total window count, because we are having the same reference pointer PTR in that sense. Also, please remember for Fortran that you need to put the protection call mpif syncreg every time that you use the synchronization fence. Now we are going to take a look at a different approach. We have seen that the memory can be contiguous inside one shared memory node, but we can actually have non-contiguous shared memory. This is beneficial in terms of performance for some reasons, particularly in CC NUMA systems, when we are having different domains and we may be hitting the page boundaries, so that we need in some occasions some padding data that will be able to have some benefits in terms of cache and also for usual operation of the system. This has been proven in a study performed and published that is indicated in the lower part of the slide. So we are having this benefit in terms of performance, but still it is a bit trickier to get to access the memory, because we are not having the same base address anymore in all the processes. We are going to take a look at this right now, because if we have this creation, we have just assume the call to MPI com split type as before, and now we are creating the window with an info variable, which has been created with a log shared non-contig flag as true. Before we had created the window with null info, but now we are using this info value to actually indicate that we want non-contiguous memory. When we have this, then we are changing the reference to the base pointer. It is something that we can actually not refer generally in every process, and therefore if we want to understand where the base pointer of each of the processes is beginning, then we have to use MPI WinShared query. And with this we will take the advantage that the order of the ranks has been preserved in the creation of the split communicators, the SMP communicators, and we can query the shared window in the left neighbor by indicating myRank in the shared memory communicator -1, and the right neighbor by myRank SM +1, as you can see in the code part. Later on, we can refer to the correct value that we want to find by selecting the correct base pointer and then the right address, which will be the last one in the leftmost or in the left neighbor, and the first one in the right neighbor. On top of this, we need to take into account some issues that may happen from a technical perspective. The use of shared windows is generally possible, and there should be no problem with an MPI implementation, but the system itself may impose some limitations at OS level about the amount of shared memory windows and also the total size of the memory windows. This is something that may happen in systems, for example, that provide shared memory support based on POSIX shared memory that will reserve by default maybe 25% of the physical memory and define the maximum of 2043 windows. Just also as a default limit inside the other MPI implementations. So this is something that goes a lot into the actual implementation of the MPI library and the configuration of the system. So we need to make sure that it is possible, if we want to really define a high number of windows and also a really large size for those windows, that we are actually not hitting any limit and that we are able to support this without getting unexpected errors. Also, it's important to remember that MPI COM-split type may return in some older MPI implementators just MPI COM-self and simply not perform the split into shared memory islands that we want to do. However, in the most recent approaches, this shouldn't be the case. And now we are going to see how it is possible to split the communicator without using effectively the function MPI COM-split type. We are seeing that this function is creating the shared memory communicators, but we actually can use the normal MPI COM-split and in determining the correct coloring, the correct tag for the split, so that we obtain the real distribution that we want to or we intend to have in the case of shared memory islands. This is something that can be useful when we have some particular conditions in the CC/NUMA architecture and we want to control how to use this how to define these communicators properly. However, this is also not guaranteed that MPI win allocate shared would work on the whole SMP node as expected. This is not guaranteed by the standard itself. And alternatively, we could also use a combination of MPI COM-split type and also create some islands within the shared memory island created by COM-split type. We could use COM-split also to define more fine-grained islands within the shared memory node so that we can tune our performance and possibly create a communicator for each socket that we can use even more efficiently the shared memory communication, and then combine this with the distributed memory communication too. And from this point on, we are ready to have the first exercises on shared memory.